Because I gave them Lucy's phone number and they were asking like my schedule and stuff, so they just came like after practice. Yeah,
All right. How's everyone feeling today? Glad to hear. Let's see. Happy Wednesday. Any questions about anything at all before we get started today? All right. Well, my computer is deciding to wake up very slowly today. So let me remind myself where we leave off. We have been talking about what physics is, scientific method, data and measurement, and now we are going to try to review all of the math knowledge that you could possibly need to know for this course before we start learning about concepts and how math describes them, how we use math to describe the universe. In talking about data, I've attempted to make it clear that because physics is inevitably tied up in data, we cannot avoid using math, so we have to remind ourselves what sorts of algebra we need to be using. My computer's being very weird right now. That's throwing me for a loop, if I'm being honest. Yes?
We don't have lab today, right?
Correct. There is no lab today. There is no lab this week at all due to MLK Day canceling Monday, and there now being a Monday section of the lab. In general, if class doesn't meet on Monday for whatever reason, I will just can lab that week because I don't want one group getting ahead of the others. The goal is for every lab within a week to be the same activity. So, no lab at all this week. We'll start labs next week. Still revising my schedule for that, but we'll find out what we're doing next week. As an additional reminder about lab, every lab is completely self-contained. You don't have to prep anything ahead of time. You don't have to, there won't be anything that you take home to work on afterwards. You show up, you do the self-contained activity with your table mates, and then you go home. So, when you do start coming to lab next Monday, Tuesday, or Wednesday, just bring your notes and your calculator and your a team spirit. Anything else in your minds for right now? All right, so, as I said, we cannot avoid doing math in science, so let us try to review every possible math thing that you have definitely seen before that you'll use in this class just to set the foundation. I want to talk about this before we look at any new formulas or concepts to make sure that whenever I show you a formula and start doing things to it, the things that we do make sense now rather than later. So, in this class, we like formulas, specifically algebraic formulas. And so, here's one of the first formulas we're going to be looking at. I believe I've showed it once already. This is called Newton's second law, net force equals mass times acceleration. And as we'll talk about in a week or so, what this means for our daily life is that if you have an object with mass, and every object has mass, and you want to accelerate it to make it start moving, you have to exert force on it. And the rate of change in its motion depends not only on its mass, but also on the amount of force you exert on something. If something has a lot of mass, it takes a lot of force to make it go fast. Which is why usually trying to push a boulder with your bare hands doesn't go very well. Boulders have a lot of mass. If you exert a teeny tiny amount of force, it's going to accelerate a teeny tiny amount, if at all. So, in physics we have formulas. I will try to narrate what each thing within the formula means in terms of normal descriptive language, but we still have to be able to manipulate that formula algebraically. For example, let's say that as a sample problem, we have a boulder that has a mass of 1,000 kilograms. That would be like 5 of me. And we want to make that boulder start moving. We want that boulder to accelerate. And all we have available to us is ourself and our own human muscles. Let's say that you, as a human being, are able to output, let's just say, using your arms, 500 newtons of force. A newton is about 1/5 of a pound. So, this is the force we can output with our normal human arm muscles. This is the mass of the boulder. What will the rate of acceleration of the boulder be if we exert that force on it? Using what you know about math and algebra, how would you proceed from here to determine what A is equal to? Right, we're going to divide both sides by 1,000. On the left, that's going to give us 500 divided by 1,000. On the right, that's going to give us 1,000 times A over 1,000. And anything divided by itself just cancels out. So what we've basically done here is send something from the right to the underside of the left. So 500 over 1,000 equals A. So the rate of acceleration of this boulder will be 0.5 meters per second squared. And that's how we utilize algebra in this course. Pretty much every formula I give you, we will be rearranging algebra to try to solve for something in it. And so it helps to remind ourselves the order of operations that we use in order to do algebra. Is PEMDAS unfamiliar to anyone in the room? Okay, just check. Once again, just as review, this acronym stands for the order in which you tend to perform math operations on an equation or a function. Let us practice that slightly. I'm going to put PEMDAS on the board itself, just to be able to refer to it when we slide, it doesn't show it. Here we have two math functions. And using the correct order of operations, I'd like you guys to ponder what they should be equal to. I'll give you guys a couple minutes to work both either on your own or amongst yourselves to determine what these are mathematically equal to, and then we'll review how to do them properly. see. 2, 3. All right. Let's look first at the one on the left. Now, order of operations, PEMDAS, stands for parentheses, exponent, multiplication, division, addition, subtraction. And you want to go through the order from left to right to solve something like this. So there's no parentheses in this one. There's no exponents in this one. So we are good to skip straight to PEMDAS. Now, the thing to note about it, the order, is that multiplication, division, and addition, subtraction have the same, well, multiplication and division have the same priority as each other, and addition, subtraction have the same priority as each other. So the M only really comes before the D and the A before the S, just so that it spells out a word that can be pronounced in English. But you could just as reliably write PEDMASA, technically speaking. What that means for this is, we're going to ignore the minus and the plus for now. We're instead going to look at the division and the multiplication first. So 18 over 3 actually is not a fully divisible number, so I'll write that out as a fraction for right now. Minus 7 plus, and then we've got 2 times 5, which is 10. So again, the M and the D have the same priority as each other, so we can go through both steps at once. Yes?
Couldn't 18 by 3 be 6?
You know what, you're right. I had a brain fart there. 18 by 3 is 6. Thank you. Please call me out when I do silly things like that. 18 by 3 is 6. It feels like a Monday for my brain. Okay, thank you. Now, the last step, addition, subtraction, all is the same priority. So we're fine to proceed with any one sign that we want to first. So 6 minus 7, that's going to be negative 1. Negative 1 plus positive 10 is 9. Ignoring that, how's this feel? All right. Now, let's look at the funkier looking one. This does have parentheses and exponents in it. Maybe someone's trying to communicate in Morse code. Does anyone actually know Morse? I apologize if that becomes distracting. Not much I can do about it at the moment. So within this one, there's slightly more things to do. In addition, like just because there's parentheses and exponents, but also there's x's and y's in here. Now conveniently, we were told what x and y are equal to. So the first thing we should do is substitute in all of the values that we know. So I'll rewrite this. We've got 2 times x, x's are equal to 1, minus 4 times y, y's are equal to 5. 1 times 5. Note here, the squared is attached to the y, so that's going to be 5 squared. Close parentheses, all divided by 3 times 1 minus 6 times 5 over, here again, the cubed is on the x, so that'll be 1 cubed times y. So we've plugged in everything that we know. There's no unknowns left. So all we have to do is solve for one final value. Order of operations tells us, first, parentheses. And we've got 2 fairly big sets of parentheses here. What that means is we should figure out what this one big thing is, and then what this second big thing is before we try to do this division sign in the middle. Like ultimately, this is going to be one thing divided by some other thing. And the parentheses in this case is just reminding us, figure out what this is before attempting to divide it by whatever this is. Does that make sense? Okay. So now, once you establish the presence of parentheses You then look within the parentheses and proceed down the line from there. So first up is exponent. Within each of these sets of parentheses, there is one exponent apiece. That's the 5 squared and the 1 cubed. You should not necessarily erase what's in your notes, but I don't have a whole lot of board space, so I'm just going to show by transforming things one piece at a time. The 5 cubed, sorry, that's 5 squared. The 5 squared. What is 5 to the second power? 25, very good. And what is 1 to the third power? It's 1. Yeah. 1 to any power besides 0. No, 0. Yeah, 1 to any power, so 1. So that's the exponent step solved. Question so far? All right, next is multiplication and division. I would prefer at this point to multiply each of these pairs into each other, so we got fewer terms floating around. So I'm just going to rewrite all of this now. 2 times 1 is 2, minus 4 times 5 is 20. Now note, minus 4 times 5. You can think of this as either positive 4 times positive 5 is 20, and then we are going to subtract positive 20 from something. But you can also think of it as negative 4 times positive 5. Either way, it should say negative 20 here. And then, on the underside, 1 times positive 25 is positive 25. So that's the first set of parentheses done. On the bottom, 3 times 1 is 3, minus 6 times 5 is 30, and then 1 times 5 is 5. So fewer terms floating around now. Questions thus far? All right. Now, from here, you could go one of 2 different ways. Because multiplication and division are all supposed to happen at once. We've got fractions within our fraction here, even inside the parentheses. We've got this whole top piece divided by something, and then this divided by something. So you could do division now and divide 25 into this and 5 into this, in which case you'd have a fraction minus a fraction. That would be a totally valid way of proceeding from here. Now, my preferred method would actually at this step be to figure out what 2 minus 20 is and 3 minus 30 is first, before dividing. And the order of operations does account for that. But you could proceed either way from here. You could do the division first and have a fraction minus a fraction, but you could also do the subtraction first and just have one fraction. You can kind of think of the numerator as its own kind of parentheses term, and you'd just be figuring out the subtraction within that parentheses first. Either method works. Don't want to discount one or the other. I am light on board space today. I shouldn't have made it such a big fraction. If we did the subtraction for each step first, 2 minus 20, negative 18, over 25, close parentheses. And then down here, 3 minus 30, negative 27 over 5. Does that make sense? Feel good? Better question, does that not make sense or not feel good? Okay. So I've been proceeding from here to here to here to here. Normally I try to arrange things vertically, but this one's taller than it is wide. So now we're at this step. And if we're following the order of operations correctly at this point, we should, within the parentheses, do the division, which would give us weird decimal values, but let's show what that looks like, show what that option would give us. So on your calculators, if you do negative 18 divided by 25, you should get negative 0.72. And in the denominator fraction, negative 27 divided by 5, negative 5.4. Now, everything within each individual set of parentheses has now been totally simplified. You still arrive at these two same numbers if you instead turned these into two fractions apiece and then did the subtraction. You should still end up at the same place. Now that everything in the parentheses is solved, we can just treat this as number over number and do the division as normal. Now, if you're typing this into your calculator, I would honestly try to type it in as it's presented, negative 0.72 divided by negative 5.4. Note what's going to happen to the negatives in this particular case. Cancel out, very good. And that should give you something to the effect of 0.13 repeating. By repeating, I mean the 3 is just going to go on for as many digits as your calculator allows. The overline above the 3 is the math shorthand way of writing that. And math fraction. My calculator can also tell me that that's equivalent to 2 over 15. How's this one feel? Is math scary? Okay, cool, good to hear. Real quick, I'd just like to demonstrate a slightly alternate tactic, and this will be referenced in the next slide if you're following along with the notes I posted in Brightspace. These two numbers are these two fractions solved, but I just want to remind you of an alternate method that would work, because when you divide by a fraction, that would be the same as multiplying by the inverse of that fraction. So an alternative method you could choose to employ here is to rewrite this as negative 18 over 25 times negative 5 over 27. Dividing by a fraction is the same as multiplying by the inverse of that fraction. Does that sound familiar? Okay. Now, if one did that, we would have negative 18 times negative 5 divided by 25 times 27, because if you are multiplying fractions, it's the entire numerator, well, it's both numerators multiplied together over both denominators multiplied together. So as long as it's one times the other, that's not, you don't want to cross multiply there, that's something else entirely. If it's fraction times fraction, it's the top piece times the top piece divided by the bottom piece times the bottom piece. And just to prove how that works, negative 18 times negative 5, close parentheses, divided by 25 over 27, sorry, times 27. Once again, 1.3 repeating. So, produces the same result. So, there's usually more than one right way to do math in this class, and I don't want to discourage any particular method over the other as long as it works. Often whatever I do on the board when we are doing math doesn't have to be the one correct way. And it's also one reason why when you're working on a test and I ask a math question, I encourage you to always show all of your work, not just because I know at this point, like when I was in school, grade to high school, I always had a hard time showing my work because I would arrive at a number in my brain, I'd write it down, and I would hate having to spend the time showing where the number came from. It's a pain, and I never liked it. But in this class, I promise showing your work shows a particular purpose. Because if you just write down one number answer for a math question and you're wrong, then you're up a creek without a paddle. Because if you showed all your work, I can see where you might have made a mistake and give you partial credit. But if you just write a number and it's wrong, then there's not much more I can do for you. So it's not just about justifying where the answer came from. It's not necessarily that I think you're cheating, it's that showing your work is your protection against making mistakes. I give partial credit for everything you write. It is possible on one of my tests to never get a math question completely, totally correct and to still get an A on the test. If you write all your work out, show everything, and just make like one teeny mistake, maybe you hit a wrong button on your calculator, maybe you put a negative where it didn't need to go, as long as your setup is right and I can see that you understand what's going on, but you just made one tiny math mistake, you'll still get most of your points. Like, if it's a 10-point math question, and my test will always tell you how many points the question is worth. If it's a 10-point math question, you just messed up like one tiny thing, I'll give you 9 out of 10 points, as long as you showed all your work, showed that you understand what's happening. And a 9 out of 10 is still an A in this class. But if you just write -2, and the answer's supposed to be +3, I'll give you a point for the answer, but that'd be a 1 out of 10. So, show your work to protect yourself, just in case. Not that I believe you're going to make mistakes, but you know, it's kind of inevitable. Does that make sense? All right. Questions before moving on? All right. Got off a little bit of a tangent there. If you're following along in the notes that I posted, the next slide kind of just goes over the fraction stuff that I just mentioned. When multiplying fractions, it's always numerator term times numerator term divided by denominator term by denominator term. This piece here references again, dividing by a fraction is the same as multiplying by its inverse. I will point out though that adding fractions doesn't quite work that way. If you're adding fractions, you have to do the least common denominator thing. And there's a lot of different formulas in this class, lots of different ways that math will need to be done, so it's important to remember how all of these work. Is there any questions with the information currently on screen? All right. Now, the order of operations as it's normally written is all well and good. However, there's a bit of a flaw with it. Well, it requires a different way of thinking. If you are performing algebra on a formula and you have to solve for an unknown that's buried deep within the question. For example, say this is your math expression given. 5 times, open parentheses, 3 minus x squared, close parentheses, equals 10. And say your goal is to solve for x equals number. That's not necessarily a physics formula, but the math questions in this class might work fairly similarly. You'd be expected to use a formula, but be given all the numbers except for one thing in that formula, and you have to rearrange for the one thing that you're missing. I showed something with Newton's second law earlier, but as a different example, another pretty common physics formula. This is the formula for displacement if an object is accelerating. We'll talk about this in a week or so, just demonstrating as an example. You're going to move a certain distance over time based on your initial velocity and your acceleration. And let's say that you're talking about, a car that's driving, 2 kilometers over a certain amount of time, and I ask what is the car's acceleration over that time, assuming that I tell you something to plug in here, here, and here, and you have to solve for the A term. The goal would be to eventually end up at A equals something, and one has to use algebra and the order of operations to send everything except the A over to the other side to get to that point of A equals number. One still has to use the order of operations to do that, but I find kind of weirdly that sometimes you have to kind of think about that order backwards. Let's do an example. We've got that one up there. Let's work it together as an example. So our objective is to get x equals something. And the order of operations is going to help inform us as to how we're going to send all these things over to the other side. Main thing to note for algebra is always whatever you do to one side, you have to do the exact same thing to the other. So, order of operations normally would say, look within the parentheses, solve exponents within the parentheses, and then multiplication, division, addition, subtraction. Now, within this set of parentheses, we have the x squared, and, well, x is the thing we want to know. We can't really square that yet because we don't know what it is. Our goal is to get that eventually by itself. So, instead of looking within the parentheses first, I would actually advise, I've got it written up there as SADMET, working a little bit backwards. Because right now, this x is trapped within both the exponent and within the parentheses. We have to kind of dismantle everything on our way there. The only way to get rid of these parentheses is to either distribute the 5 in or send it to the other side. Technically, either would work, but I think sending it to the other side is the better idea because that just gets it out of the left side completely. And our goal was to send things from the left to the right since the left is where the x is. And note, that first step would be division, not parentheses. And that's because, again, in dismantling one side, sending pieces to the other, we're kind of going backwards. There's nothing we need to add and subtract from both sides yet. So instead, we move on to what needs to be multiplied, divided away from both sides first, before we can then break down the parentheses and the exponent that the x is stuck inside of. So, first thing we'll do, divide 5 from both sides. That'll cancel it on the left and leave the right side as 10 over 5. And so, the left side will simplify to 3 minus x squared equals 2. All right so far? All right, now, these parentheses are now pointless. There's nothing being multiplied into the parentheses. They may as well just not exist. So at this point, we can just get rid of them. And now that those parentheses are gone, we can work back through the steps again. We still want x by itself, but we can't do anything about that squared until we get rid of its friend here. So if this positive 3 is just hanging out here on the left, what do we have to do to get rid of it? Subtract 3 from both sides. So that leaves us with negative x squared equals 2 minus 3. Now, if you have a square and you want to get rid of it, what do you have to do to both sides? Square root. Very good. Now, do we want to take the square root of negative x? No. And additionally, this isn't, I want you to know, this is not the square root, this is not negative x squared necessarily. This is a negative sign times x squared. So that negative is not bound to the x at all. Because note, it was originally 3 minus x squared. So the negative is not inherent to the x squared. And that means we can get rid of it too. How do you get rid of a negative you don't want? We can either divide both sides by -1 or technically multiply both sides by -1. That will, both will accomplish the same thing. Let's do division. Negative, like this negative is basically -1 times x squared, so those will cancel. That'll leave the right as 2 minus 3 over -1. Which, just kind of skip ahead slightly. X squared equals 2 minus 3 over -1. That's -1 over -1, which is 1. So x squared equals 1, technically. And now we can freely take care of that exponent and take the square root of both sides. Note though, you have to do that to both sides. So that's square root of x squared equals square root of 1. Square root of anything squared is just itself. So that'll turn the left into x. And what's the square root of 1? 1. So, after all that, we've determined that for that equation to be true, x must equal 1. At this point, it's usually a good idea to double check your work. We can take that 1, plug it in here, and make sure that it makes sense. So, 1 squared is 1, 3 minus 1 is +2 times 5 is 10. So, make sense? Feel all right? Okay. Again, any formula I give you in this class can be treated similarly. This class is not going to be purely algebra focused, but it is still important to understand the algebra that we are going to be doing. This is going to be both concept-driven class, and the math will inform the concepts. Does that feel all right? All right. Just one sec. Yes. Now, we don't have very long, and I'm not going to hold you up, but just as one last thing before we head out for the day, take a look at these, see how many of them you can work on either on your own or amongst yourselves before we break for the day. How you guys feel? A couple notes about each of these before we head out for the day. First one, goal is to get x by itself. We gotta send away everything that is not x. Dividing by 0.5 is the same as multiplying by 2. 2 squared is 4, so multiply by 4, we end up with a pretty big number. The middle one, main thing I want you to remember here is that the distributive property is a thing that exists. So if there's ever something with the same, two things with the same variable in them being added together, you can distribute the common variable out, simplify the other two terms. 5m plus 20m is 25m. Also positive, sorry, negative times negative is positive. And then the last one is technically the same formula I showed you a second ago, just with values plugged in. A couple things to note here. 0 times anything is 0, even if that kills a variable, it goes away. And technically the way that I wrote this, you end up taking the square root of a negative, which your calculator is not happy about. So in terms of physics, that means the situation described here is not possible. Yes?
Where'd you get 0.15 from?
Point. Oh. That was a mistake. Somehow my brain turned a negative into a point. So actually, this is not an error message. My bad. I forgot the reason I wrote that one in. Thank you. Please call me out on my mistakes. I'm human. I do make them. So negative 15 divided by negative 4.9 is actually a positive number. Square root of that. So we actually do get a real number, 1.75 seconds. I know it's seconds because I solved for time and I know what formula that is. Okay, thank you. Now, we have all semester to make sure that this algebra feels good, and in fact, lab next week will be more practice before we, again, start applying that information to physical concepts. Do you have any questions or anything? Does everyone come back?
Have a good one.
Yes.
Just want to give you this